I'm Michael. Today I will be giving a hands-on session on static analysis by abstract interpretation. So you will get to practice a lot of the things that you guys learned in the last, I guess, 4 or so sessions. The way this is going to work is that it will be very interactive, and hopefully all of you have installed this Goblint systems. So if I could get a quick show of hands, who of you has installed the system? Who of you has installed? So 1, 2, 3, 4. Okay. So later on we'll form groups, and then it will make sense to please form groups where at least one person has installed the system, because otherwise you'll be sitting around with nothing to do. So that's something you might want to keep in mind for in a little bit. So the system we will be using today is an abstract interpretation based system that is called Goblint. It's developed here at NUS and also at the Technical University of Munich and by some colleagues in Estonia. And I don't want an AI thing, let's close this. So this is a system that you can use to analyze your C or C++ programs. And what it does is it uses abstract interpretation to check all of the possible executions of this program. And at the end, it will give you either a set of warnings, which are locations where certain class of bugs could occur, or the other alternative that you get is that you basically get an all clear, and system tells you that it is mathematically proven in some sense that certain classes of bugs will not occur. Such a system is usually quite a large thing, so it consists of several components here. So we have one component, which is the front end. So think of this as your usual compiler. So it does the parsing, it translates it into some type of intermediate representation. And this is not our own project, but it's offloaded to some external component. Then we have a set of various abstract domains. So I think in the lecture you have seen the abstract domain for null versus non-null, I guess. And you have also seen the interval abstract domain, I guess. So the Goblint system has all of these, but it also has some more abstract domains. So it has generic abstract domains where you can combine various domains to get new domains. You can have domains for maps, you can have domains for sets, and all types of variations of these. And then we also have a bunch of abstract domains that are more specific to the C programming language. So for example, we have something that is called a base domain, and what you can think of as this is a map from variables to some abstract domain for this type of variable. So for integers could, for example, be the interval domain that you've seen in class. For pointers, it could be points to sets and so on. And all of these are collected into this, what's called the value domain. And then we also have various other domains for C intervals. For example, we have exclusion or inclusion sets. So you can think of these inclusion sets as a set that says, oh, this variable will have a value from this set. So it's either 7, 42, or 79. And as an exclusion set, you can think of saying, okay, this variable will have some value. I don't know, but I do know that it's definitely not 13. So these are these exclusion and inclusion sets. And then we also have this interval abstract domain that you have already heard of. And then on top of these abstract domains, we have various analyses that build on them. So we have analyses. So originally, the Goblint system comes from the analysis of multi-threaded C programs. So we have analyses that infer things such as the set of held mutexes, or that infer things such as how many threads are there in the system, all of these types of analyses. And then the analysis that comes most close to what you have seen already in class would be the base analysis. So this is an analysis that basically computes values for variables. And then the last thing we see or the last major type of component we have in the Goblint system are these fixed point solvers. So I think in class you've also studied some fixed point algorithms. I think you studied the synchronous iteration type of fixed point algorithm, and the Goblint system implements this, but also a whole slew of other fixed point solvers. And if you take a look at some type of diagram of how the system architecture works, then what you see in here is that we have a quite nice separation of concerns. So we have the domains, and of course our domains, well, we want to print them at some point, so they are something that's called printable. But then they also, most of them form a complete lattice. And then having these domains that form complete lattices, you can combine them with these sets or maps to get more involved abstract domains. So these are the domains that are still generic in some sense. And then based on those, you can build domains that are specific to the C programming language. So for example, this log domain that I was talking about that computes which mutexes are held at each program point, it builds on the set domain by instantiating and saying, okay, the set that you are keeping here is a set of mutexes. And similar, this base domain builds on this map domain or functor here by saying, okay, we actually have a map from variables to values. Then these C domains are in turn used by the analyses. So we have them here. So as I said, we have a mutex analysis, that would track the set of mutexes. We have a base analysis that tracks sets of values, and we have a whole bunch more of analyses. And what you can think about these analyses is basically they are a collection of the abstract transfer functions. So if you remember from the lecture, we had these lattices and they have operations such as join, meet, maybe the concretization. These things live here in this domains and C domain space. And then the abstract transfer functions that you have, they live in these analyses. And in real-world systems, maybe you do not want to only analyze the mutexes that are held at the program point, but you also want to know about the values of variables. So what the Goblint system does is it can combine all of these different analyses together through something that is called the MCP. I think it's Master Control Program or something. So basically what this does is it takes all of the analysis, it's a Cartesian product, and then runs all of them together. And this MCP here itself is an analysis. So you can think of basically taking the transfer functions for each of the analysis that you have activated, and then you have a tuple of abstract values and a tuple of transfer functions, and then the transfer functions of this combined thing is that you apply the transfer function of each of the components. So the thing when you are here at this point is what you get is you get one analysis that basically has a sub-analysis, all of the things that you want to analyze. So at this interface here, what you have is a set basically you have an analysis. There's a set of transfer functions. This then is propagated further to the framework. And here we add a couple of things. I think they are not so relevant. What's maybe relevant is this hash consing thing. So this is some optimization thing. If you think back to your functional programming class, then you can make the thing more memory efficient by doing this. Perhaps not so relevant. The thing that's relevant again is this part here. So here we see this myCFG. And what this is the control flow graph that we got from the framework, from the program. Basically, we take the program, compute its control flow graph, and then this from spec functor here, it takes your analysis specification and it takes the control flow graph that you have. And then what you end up as a result of this is that you end up with the constraint system. So I think this is also the task that you will have to do in, I guess, the last homework, where you are given a control flow graph and you are told, oh, we're doing interval analysis, and you're supposed to construct the constraint system. And this is what happens in the system here when we get to this control thing. So then we have a control system, a constraint system. And what we want to do with the constraint system, well, we want to solve it. And this is where all of this stuff on the right here comes in. So those are basically different strategies to solving the constraint system. So there's not only the ones we have seen in lectures, but for different programs, different strategies have different efficiency characteristics. So this framework implements a whole lot of them, and then you can choose the one that you would like to have. And then the last component that we will see in this nice diagram here is this verifier component. What this does is basically, if you don't trust your fixed point algorithm quite that much, and you're not so sure that the thing that is computed is actually a fixed point, then what you can do at the end is you can have an independent implementation that basically iterates everything one last time and checks that you have actually reached the fixed point. And this is also the point where then the warnings, so the output that is given to the users, is generated. Are there any questions on this nice diagram here before we go to more practical things? Any questions? That does not seem to be the case. So then I can immediately tell you that you don't need to worry about this entire diagram that you're seeing here. So basically in this hands-on session, what we're focusing on is somehow the top half. So we will basically, from these domains that are already there, we will build our own C domain here, and then we will build our own analyses. But all of these considerations about the framework, we will not have to deal with them here because they have been offloaded to the Goblint system, and we can build on all the stuff that's already there. And this is also nice when you're doing research on the system. You have a nice separation of concerns. So you can work on fixed point algorithm if that's your cup of tea, or you can work on these analyses, and you don't need to touch all of the parts all of the time. Okay, so maybe let's also see what the system looks like in action. So I have prepared a small program here. The question is, can everybody see this? And the answer is probably not. So let's see. Increase editor font size. Can you guys see it now, or is it still too small? Still too small? Okay. How about now? Good. Okay, so this is a small C program, and what we can see in this program is not that interesting. We have a main function that has two variables, so there is this I and there's this j, and we initialize I to 25 and j we initialize to 0. And then what we do is we somehow increase this j here, then we check if j is greater than 25, and if it is, then we set I to minus 42. And if j is less than 25, while j is less than 25, we increment it. And then here we basically have checks that we want the system to prove. So here we want the system to prove that, well, I is 25. And we also want the system to prove that j is greater or equal to 25. And in here, these are these Goblint check annotations rather than asserts, because assert in C means that program execution terminates if the assert fails. And here we basically only want to inspect the result that the system has, but we don't want to modify the program such that program execution is terminated. Then down here we have another thing. We basically take a pointer to this variable j, and then if basically this random value happens to be 1, then we set the pointer to null, and then later on we pass this pointer to this function fun here. And in the function fun, we also have a check, namely we check whether dereferencing this pointer will give us something that's greater or equal to 25. Okay, now what we can do is we can basically run Goblint on this program. And you can do it like this. And I guess now we have the same problem that nobody can see the stuff down here. Can I also increase? No. Does someone know how to increase the font size in the terminal?
The terminal increase font size.
Ah. Ah, there you go. Can everybody see it or still too small? Okay, looks good. So basically what the system tells us now is that it is able to show that this assertion here holds, where I is 25. So here we get this message success, assert I is 25 will succeed. And then we also get the message here that j greater or equal to 25 is unknown. So the system in the default configuration cannot prove this property. Then the other thing that's interesting is here. This is one of the other things that the system can show. It can sometimes prove that code is unreachable. So for example, here, if we look at this, j is greater than 25. If we look at the program, then we know that j will be 7 at this program point. So the system here succeeded in showing that this program point here in line 13 is unreachable. And the other interesting thing is we had this function call here where we called fun with this pointer. And the system has established that the pointer can potentially be null. So it gives us a warning here where we say, okay, in line 3, you need to be careful because you may be dereferencing a null pointer. And it also gives us a warning in this line 3 that this assertion that PTR is greater or equal to 25 is not known. Now, we are maybe somewhat unhappy with this result because we actually wanted the system to show that j is greater or equal to 25. And if we look at the code, I think we should be fairly certain that this assertion should actually hold. So what we might want to do is we might want to inspect what the system has reasoned internally. And there is an option to do this by basically passing this HTML flag to the system. So now we are also generating an HTML report, and then we can open this up. Why do I have 25 Zoom logins? So we can open up this report. And what it gives us is a view that looks somewhat like this. So let me see if I can increase the font size again. Yes. So it gives us a view somewhat like this. And here we can inspect the results of the analysis. So for example, we can say, oh, I want to know what has the static analyzer computed for this program point 10. And I can go in here and there's a lot of things going on, but basically what I'm interested here is this part where it says base. And here we see that the analyzer has computed for this program point in line 10 that we're looking at, that the value of I is 25 and that the value of j is 0. And yes, and for the pointer here, we don't know anything about the value yet. And then we can continue. So here we also see this warning. So in this case, it was this warning here that basically this if will never be true. So we get this warning, this condition is always known. And then if we go down here, we can see this assert that actually succeeds. And here we see that this I, we can show that has the value 25. And then if we go here to this check, we see that the information that the system has for this j here is not precise enough to conclude that it's greater or equal to 25. Because what we have computed here is we know that it's not 0, and we know that it's some type of int, but we don't know more. And the reason for this is that here we used an abstract domain that's not so powerful. So basically the abstract domain here we have here, that's constant propagation. So this is also something you'll see in the homework, I guess. So what it does, if you know that in every execution, this j will have a constant value, then you get this constant value. And the other thing it does is this exclusion set. So it can tell you, okay, here's a couple of values that it will definitely not have. And here in this case, we're in this case where we basically only know that this j will not be 0. So before we fix this, let me show you another view that you might find helpful later on when you are actually implementing your analysis yourself. And to do this, we can go basically click on the function. And what this gives us is the control flow graph. So this is the control flow graph for our function, and we have all of the nodes. And what we can do here is we can click on one of these nodes to inspect the state that the system has computed for this node. So let's maybe go here. And here we see that we have computed that I is 25 and j is 7. The other interesting thing is in this view, you will also see for which nodes the system has computed that they are unreachable, because they will be marked in this orange color here. So here we know, because j is 7, we know that this guard, where we check that j is greater than 25, cannot be evaluated true. So we compute a value of bottom here, which denotes unreachability. Okay, so then any questions up to this point? That does not seem to be the case. Then let us continue with fixing this, with fixing our analysis. So we really want to show that this thing here holds. So one of the things that we can always do is we can basically make the analysis more expensive by enabling more expressive domains. And the question is, have you maybe in lecture seen a domain that might be helpful to establishing that this j will be greater or equal to 25? Have you heard of any domains that could express such a property? So I think we had this domain where we study whether something is null or not null. Do you think that this would be a helpful domain to activate here? Probably not. Any other domains we have seen in lecture that might be helpful to express such things? There's not so many domains you guys have seen, so I assume all of you are internally shouting interval domain. So maybe let's do this. So we can pass this option, enable Anna int interval. And what this gives us, it additionally enables the interval domain. So if we look at our results again, then here we can see that this assertion will now succeed. So we have succeeded in establishing that j will be greater or equal to 25. And if we look at any of these program points, so for example here, we can see that we now have this thing that I was telling you about earlier, that we have not only one abstract domain, but a combination of them. And here we see that our propagation of constants and this exclusion sets, it's still not very helpful. So it still says that we don't know anything about this value, but also we see here that our interval domain was successful in establishing that the values are now between 7 and 24. And of course, this assertion here will now succeed. So we are able to show that dereferencing the pointer will be something that is greater or equal to 25, provided that it's not null, because we still have this warning here that you may dereference a null pointer. And this is actually a warning that we cannot get rid of by enabling more powerful abstract domains, because it's a problem that is also there in the concrete. Are there any questions on this? Yes.
About the random function, is a function always
So the random function here is the random function from the standard library.
I mean, because we place another function that always true or?
Yeah, you know what? Let's try it. So let's maybe. Which one do you want? Always true or always false?
Always false.
Always false. Yes. So we can check the program. Okay. Yes, I should write the same thing. Yeah. So in this case, we were able to show that we will never dereference a null pointer here because we are able to establish that this assignment in line 29 is dead. Any more questions this far? Okay, then let's move on to the part where you will actually get to do something. And so we have seen that this Goblint system has many analysis, but one type of analysis that is still definitely missing, and today you will get to fix this, is a taint analysis. So a taint analysis is an analysis that's quite useful, for example, for security-related properties. And the basic question that it answers is whether information that is somehow tainted can flow to somewhere where it's not supposed to flow. So an example of this would be that you have a system that takes some input from the user and then uses the input from the user in an SQL query. And as you've probably heard in your security class, sometimes this can lead to problems if you don't ensure that the input from the user is properly escaped. So then a taint analysis question might be, can something that the user gives me somehow end up being integrated into an SQL query? Or another place where taint information can be useful is if you're trying to detect whether buffer overflows can occur. So for example, you take some sort of length argument from the user, and then if you use this without validating anything, then this may also be a problem. Or another problem is some type of key exfiltration. So basically, if you have somewhere in your system, you have a private key, and then there's a way for this key information to flow to something that is exposed to the public, say sent over the network or output in the console, then this could also be a problem, and this would be something that you can detect with a taint analysis. And to sum it up more generally, the idea is a variable is tainted if it somehow may contain information that originates from something that is called a source. So in our first example with this SQL injection, the source would be something that comes from the user. And then the analysis should warn whenever a tainted variable reaches a sink. So in our example with this SQL injection, this would be if the tainted variable somehow flows into the string that is sent off to the database. And there's a small caveat here. So the Goblint system, we are not experts on taint analysis. And here we will only build a very basic taint analysis. And we will assume that there's no sanitizers. So basically, there's no way to make a variable safe after it has been tainted other than completely overwriting it. We will assume that we don't care about implicit flow. So if you don't know what implicit flow is, you don't need to care at this point. And the other thing we do is we assume that taints occur only at the level of variables. So the complete variable will be tainted, and we do not care about the specific offsets, for example. And then the other caveat is that we don't have so much time, so we will only be considering some tiny subset of the C programming language, this mini C. And in this mini C, we will assume that we, for example, don't have any multi-threading. And we will for now also assume that we don't really have pointers. So this is something that will make it tractable for you guys to actually implement this analysis. So this we have already seen before. What's important here is this additional information that I'm giving you guys, namely where you can find these specific components. So for example, we have talked about these generic functors that take an abstract domain and make it into another abstract domain. And these things you can find in the source directory of the system in the domains folder. And then also we have these domains that are specific to C, and these you can find in the source folder in C domains. And yes, so these are the analysis we have seen so far, and the analysis you will be adding will be this taint analysis. That's the architecture. And then I will help you get started by taking a look at the file that you will later be asked to expand. And this is this file here. So it's OCaml, but there's no need to be scared of it. If you have any OCaml questions, I'm here to help you guys through it. So the idea here is that you basically come up with the conceptual things, and then if it's an implementation thing of how to write it down in OCaml, I'm happy to help. So this analysis, what it does is we have this analysis specification, and the first thing that you guys will need to think about is this, where it says here module D. So here you need to define what your lattice should be. So if you think about this taint analysis problem, then you will need to decide, okay, what information do I want to track at each program point to be able to answer the question whether tainted information flows to a sink. These things here you can completely leave alone. So this is how the system does interprocedural analysis, but this is already set up for all of you. And then here we have also defined some helpful functions that we think you might want to use later on. So there's this function isExpressionTainted, and what you do is you provide it with basically an element from your lattice, from your domain that you have defined, and with an expression. And then what is it supposed to tell you is whether this expression contains anything that is tainted. And here there are some to-dos that you will need to complete. And then the other thing that's important is this part here, where it says transfer functions. So what these are the abstract transfer functions that you have seen in the lecture. So basically they tell you if I have some state before before executing a statement, and I execute this type of statement, what will be the state after executing it? So the most classical one is maybe this assignment. So what this does is it basically is this type of thing where you assign to some L-val. So this is the expression on the left-hand side. You assign some R-val. And we have already set up some things here. So basically what the state gives you is it gives you your abstract value before the statement. And then what you need to do is you need to see what is on the left-hand side of your expression, and then you need to appropriately propagate the taint information. Then the other thing that's interesting, or the other thing that's here, is the branch. As we said, we're not dealing with implicit flows here, so the branch you can simply leave alone as it is. Then we have this function special here. And what it does is it's a transfer function for calling a special function. And the special functions are things from the C standard and these types of things. And in our setting here, we are treating source and sink functions as special functions. So what you should do here is you should check whether this special function that you're calling is a source or a sink. And then depending on this, you either need to update your abstract state to reflect what has happened, or you need to produce a warning. And if you want to produce a warning to the user, you can use this m.warn, which is the facility by which Goblint produces user-facing warnings. And you can search for occurrences of this pattern in the code. It's quite simple. You basically give it a string, and this is all you need to do. Then the other two interesting functions are basically return and enter here. So return basically handles returning from a function. And here we have set it up such that it's a bit simpler. And basically what we say here, okay, if the return value is tainted, then you can use a special extra variable that we have introduced, and you should mark this special extra variable as tainted. And then also in the combine assign later on. So this is basically dealing with assigning the return value. What you would do is you would say, oh, if the special value was tainted, then I will also mark the left-hand side as tainted. And then the last function that I want to show you before you can get started is this enter function. And what the enter function computes is it computes the entry state or the abstract entry state of the called function. So you get to a function call with some taint information. And then basically what you need to do is you need to create the initial taintedness information for your function call. And the way this works is you look at the formals that you have and you look at the actuals. And basically, if any of the actuals or if the actual corresponding to a formal is tainted, then you should also mark the formal as tainted. You will see this in a second. Any questions this far? I guess not. So the other thing I want to show you is you don't need to program without any tests. So we have set up some tests for you. If I can find them, I think they're here, yes. Are they here? No, they're in tutorials. So this is the type of thing that after today's session, your analysis should be able to show. So here we have marked this get char function as a taint source, and we have marked put char as a taint sink, as well as this print int function. We have also marked this as a sink. And then basically here in the program, we can see that we get X, we do get char. So this should mean that X is now tainted. And then we do a couple of print statements. So here we only print constants. So we expect your analysis to not produce any warnings. Then we print this variable X that is tainted. So your analysis should produce warnings. Then here we print this expression X plus 7. So this should also, it involves X. So it also should also produce a warning. And then we see a whole bunch of such cases. And then what you can do is you can run your analysis with this command right here. And then here you will see that right now, nothing is implemented yet. So we see that here in line 18, we were supposed to produce a warning, but we actually did not produce a warning yet. So this is something that should be fixed later on when you have implemented these things. And if you want to run one of these on their own, then you can basically call this script, this regtest sh, and then you supply 99 for tutorials and the name of the test. And then you basically, no, okay, you should use this, this script here. Okay. Any further questions up to this point? I guess not. So I think so to help you get started, let's maybe do the first step together here. And if we look at this analysis here, then I said the first thing we would want to do is we would want to change our local domain, so our lattice, to be able to express the properties we're interested in. And if you recall, for this tainting, we were interested in whether a variable may be tainted or not. And one possible way to represent this would be as a set. So I could have a set of variables that may be tainted. And then if the variable is in the set, that it means that it may be tainted and the taint may propagate. And if it is not in this set, then it means that the variable is definitely not tainted. And such that you don't have to get so deeply into the framework, up here we have actually already defined basically, think of it like a class or a type that gives you a set of these variables. And the order here is also already defined in the correct way. So basically here, for this set domain of variables, what we have is that the join is the union, and the ordering is subset inclusion, and the meet is the intersection. So here you already have this var info set, which you can use as your domain. And maybe this will help you get started. So I see most of you are making good progress. However, we don't have so much time. So what I would suggest for now is that we sort of together build up one solution here, such that all of you know how the final solution would look like. So we can get started here. So the thing that we already talked about is that the first thing that we want to do is we want to, in this place, set our abstract domain to be this var info set. And then the other thing we wanted to do is here we have this helper function is expression tainted, and this gets a set of potentially tainted variables and an expression, and we want to determine whether this complete expression is already tainted. So what we already do here is we recurse over the structure of the expression, and so if we find an lval, then we go call this is lval tainted. And if this lval consists of a variable, then we are here. And now the question is, what do we want to do if we are basically have broken down our expression to a variable? How do we check if this variable is potentially tainted? Any suggestions? I think most of you got this part. How would I check this? Don't be shy, at least 95% had it. Yes, up there.
Just to check if the state of this variable is in that thing.
Right. So I can say d dot. Yeah, okay. The ChatGPT, I check whether it's in this state. So this is the only thing that I need to do here to check whether this expression is tainted. Now we continue on to our abstract transfer functions. And the first one that we hear was this assignment. And we said this is assignment where we assign the value of rval to the lval. So this is this type of assignment, lval equals rval. Now what we need to do here is we first get our set of potentially tainted variables. And then the question is, so if I have a variable on the left-hand side, what should I do? Maybe first of all in English, what do I do if I assign an expression to a variable in this taint analysis?
You just check that the expression is the R value. Right.
Okay, so you say I should do this if, okay, I need to somehow turn off the ChatGPT. This is a bit, how do I do this? Snooze, I guess. Not like this, I guess. So I check whether the expression is tainted, and I do this by supplying the state and the expression. And then what should I do if it's tainted?
And variable b then AE.
Yes. So I call d.add, and first I supply the variable, so it's v and state. So 50% of the work is done here. What do I do? First I need to correct this because it's erval and not exp. Okay, what do I do in the other case? So currently it says state here. Is this already correct, or do I need to do something else? So if the expression on the right-hand side is not tainted, what do I need to do? Remove the tainted state on the left elbow. Could you explain why?
If our value is previously tainted, non-tainted sign to clear that taint.
Yes. So I remove it from the state. Does anybody have questions about what we're doing in the assignment? Or is this clear to everybody? Maybe by show of hands, to whom is it clear? That is definitely not all hands. So those who didn't raise their hand, could you try to formulate a question?
Or you can say completely.
That's also fine, yes. Why do we remove the variable? That's a very good question. So imagine that the variable is tainted before, and now I'm assigning it something new that is not tainted. So v was tainted before, and now I set it to 17. Then I want to say, okay, now this thing is no longer tainted because I've overwritten the thing that was tainted. So this is why we remove it. Any more questions on the assign? I guess not. So then we can move on to branch. And here we're lucky because we don't need to do anything. So we now get to the case that's a bit more interesting. So we're looking at these special calls. And here we need to consider the source or sink functions. So the first thing we do, and I will do this part here already, we need to check if it's a source. And I check this by supplying this f. Then and then maybe just return this for now. So there was some questions about what this man here is. And basically it's a sort of record where the framework collects all type of things. So this is not something that we need to care about. The irrelevant part is really the caller state here, which is this set of variables. Okay, now if it's a source, what should I do? So I have found out that the function that I'm calling here is a taint source. Any idea what I need to do with this information?
Or an option, right? So if it's none, then you don't have to do anything. You can turn the caller state as it is. So how will you destructure the option and
So this elval here is the thing on the right hand, on the left hand side. So as you are suggesting, so I match it with none, and the other option is some v. So what should I do if it's none? Okay, could you elaborate why you return the caller state if it's none? Or maybe somebody else has an idea. Why do I not need to mark anything as tainted? So if the thing on the left-hand side is none, then I'm calling a function, but I'm not doing anything with the value that I get back. I simply discard it. And then I don't need to mark anything as tainted. Now for the other case, I'm calling a function that is a source, and I'm assigning it to some variable v. What should I do? What I should do in this case?
Add v to.
We should add v to the set, yes. I think it's the other way around. No. This is a bit. Okay, and then basically you have to have this case again, which, because here we say directly variable, but it could also be a pointer, but in our language we're ignoring pointers. So which is why I've added this third case here. Okay, so this is our new state. So now I have dealt with sources. Any idea of, this is a bit strange. Any idea of what I need to do for sinks? So if let me quickly reload the editor because it got stuck on this strange highlighting thing. Increase editor font size. Okay, so we have dealt with sources. What about sinks? So I'm calling a function that is a sink. What do I need to check?
The sink contains some tainted values as argument, we should have one.
Okay, so then I maybe break it up and say I check here, is any tainted? How could I check this conceptually?
To iterate over the arguments,
Mm-hmm.
there is a tainted value on that.
Right. So I can say I cheat a little bit. There's an exists function that tells me whether there exists any element in the list. And then for each of the elements, I check whether it is tainted. And for checking whether it is tainted, we have this isExp tainted function. And it takes a state and an expression. And now if something is tainted, what should I do? Raise a warning, yes. If is any tainted, then okay. And here, of course, I need to supply the list of arguments. Okay, so we should be done with our special handling. Are there any questions on what this special function of our implementation does here? So if it's completely clear to you what it does, please raise your hands. That is by far not everyone. Okay, so who completely understands what happens in the case the function is a source? Also not everyone, okay. Can anybody formulate a concrete question on the case where it is source? So the reasoning for the source case is the following. If you are calling a function that is a source, then it will give you back something that is tainted. And then what you need to do is, if you're assigning this anywhere, you need to mark this variable as tainted. So this is the reasoning for the source case. So any questions on this? And any questions on the sync case? I guess also not. So what we can do is we can try to run our example. Oh, and some tests still. Okay, yes. Need to compile. And it's nice because the first test that we had already works. So with this, what all of you have implemented is a simple, for now, for language or procedures, taint analysis. So this is already nice. And unless there are any questions on this, we want to extend it to an interprocedural analysis. Are there questions? So ideally, all of you would now be able to basically implement this on their own if it was a programming language that you guys are more familiar with, maybe. Okay, I see some nodding. Good. Then, I mean, this body function, we've already seen that we don't need to do anything. So then let's complete the part that deals with function calls. So here we have this return thing. And maybe we start out by thinking in a high level in English, what do we need to do for function calls? And we can maybe start here when we construct the start state of the function. So if I call a function with 5 arguments, when do I need to mark the arguments tainted? Any idea? So basically what I already have here is I have these 2 lists. I have the list of the formals. So these are the arguments of the functions. And then I have the list of the actuals. So this args, these are the expressions that are supplied. And basically now I go over each of the pairs of them and try to see which of the parameters of the function now need to be marked as tainted. So any suggestion for what we should do here? where it says change accumulator TS here. So we might want to change the accumulator, but in what way do we want to change it? And here we come to a place where we see that we have a formal F, and we have an expression A that is supplied to this formal F, where this expression A may be tainted. Yeah.
So you just add the formal state sorting.
Yes, this is what we need to do here. So if I supply something as the argument that may be tainted, then in the function that I'm calling, this variable is also tainted. So I can say d.add, and then I'm adding f to the accumulator. And this is all that needs to be done. So basically the start state for the procedure that I'm analyzing is obtained by iterating over all of the formals and looking at the arguments that I'm supplying and checking whether any of these arguments are potentially tainted. So now we have dealt with what we do to get the start state for the procedure. Now the other thing is we need to deal with the handling of return. And here we have this return function. Basically what we do is we match the the argument of the return. And if the return has no argument, then we don't need to taint anything. However, if we return something that is tainted, then we potentially need to mark the left-hand side of the function call as tainted. And here we have this hint that we can use the special variable return var info in place of a variable to mark it tainted. So then any suggestions for what I should do here in this case that I have an argument to the return? What do I need to check? Yeah. The previous part, the part about the enter. Okay. So what the enter was about is you have computed some set of potentially tainted variables at the place where a function is called. And now you're going into the function. And you want to know which of the arguments of the function are potentially tainted. So what you do is you look at the expressions that you're supplying as the arguments to the function, and you're checking for all of the expressions that you're supplying whether they are tainted. And if they are tainted, then the local variable inside of the function also needs to be tainted. So we can do a small example here. So let's say that we have a call to a function. A function is called f, and it takes two arguments, x, y, and we have a call, and we call it with the argument z plus 8, and the constant 42 maybe. And we know in the state before that the variable z is tainted. So what we would do is we would look at this expression and the corresponding form, and we would say, oh, the first argument that I'm supplying to this f is tainted, so I need to mark this variable x inside of the function also as potentially tainted. Does that answer your question? Okay, good. Then let's come back to our return here. So if I call return and I'm supplying an argument to the return, what do I need to check? Okay, yes. Could you explain why? Yes. So the idea is if the expression is tainted, then this will taint my caller if it has a variable there. So I check is the expression tainted, and then we said we had this cheat code here that we have this special variable return var info that we can use to simulate this. So we say this is tainted. And if the expression is not tainted, then I don't need to do anything. And now for the last part that's missing until we have completed this task here, this is this combine assign function. And basically what we are doing here is we are taking the state from the caller and the state of the callee, and we're combining them together to get the state past the function call. And okay, maybe first of all in English, any idea of what I should be doing here? When do I need to mark the left side? When do I need to mark this variable tainted that I'm assigning the result of the function call? When is this variable tainted?
When the return value is marked tainted in the return, then we should mark the L value as in. It's similar to the assign, but here the R value.
Yes, exactly. So we can modify our example a little bit here. And basically, we make this void function, we make it a function that returns an int. And we have said that, and here we are storing this into y. And now here we have a return x. So we have seen earlier that we checked whether this is tainted, and then we recorded the special, we basically recorded that the special return thing is tainted, and now we are here. And basically what we are checking is if this special return thing is tainted, then well, now we need to mark y is tainted. So the way we can do this is we first of all check, okay, let's do it the other way around. We check whether we actually have something on the left-hand side. Because it could be that we are just calling this function and getting rid of the result, and then this is boring. So we check this. If we don't have anything there, we can just return the caller state unmodified. And if we have something there, you already suggested that we should check whether this special return value is in the state. So if d.mem and the special thing, what was it called? Where was it? Return var info. And now I need to check in the state of the callee. So I check here. So what should I do if it's in this if the special thing is marked as tainted?
Just mark the L value tainted.
Yes. So we say here we add And if it's not, I don't need to do anything because it's not tainted. So let's run make again. And then all of our nice tests and tutorial pass. So we have now completed an analysis that does taint tracking, and it's also able to deal with function calls. Are there any questions on any of these functions that we have, or on any of these definitions that we have supplied here now? Or on any aspects of the taint analysis? There in the back, yes.
Right. That's all.
Caller state. Caller state is the state of the caller before the call. So it will be this thing here.
So it could be, you may or may not get return from somewhere. It's just that I can input it.
So the caller state is the state inside of the function that is doing the call. So basically it's the state before you've done the call. And the counterpart that we see here is this callee. It's called callee local, but it could also be called callee state. So this is basically the state at the end of this function here that I'm calling. And with this function, that what this combine here does is it takes this state and those states and turns it into the new state after the function. Any more questions on this or the taint analysis? I guess this is not the case. So then, thank you for taking part in this interactive session. I hope that you learned something. And I find that usually by doing this sort of implementation thing, one hopefully gets a nice feeling for what is going on inside of this abstract interpretation. And this might actually also be helpful for what's coming next.